Calculus 1 video lecture number 11 on derivatives of trigonometric functions. So before we get going, we need to have two limit formulas at our disposal that we're going to be using. The first one is the limit as theta approaches 0 of sine theta over theta equals 1. And alternatively, the limit as theta approaches 0 of theta over sine theta is also equal to 1, since the reciprocal of 1 is 1. And we have the limit as theta approaches 0 of cosine theta minus 1 over theta is equal to 0. You can't work with the reciprocal of that because remember, 1 over 0, that's not defined. But this first limit formula you can use if you have theta over sine theta or vice versa. All right, we are going to use both of these right now in the derivations to follow. So let's derive the derivative with respect to x of sine of x. Anytime we're working with trying to figure out the derivative of a new function whose derivative we don't already know or have a rule for off the top of our head, we got to go back to our definition that we used. Remember, we have the derivative with respect to x of sine of x would be the limit as h approaches 0 of sine of x plus h minus sine of x over h. All right, so first things first, I'm going to expand sine of x plus h using my angle addition formula. Do you remember it? So if you have sine of a plus b, that's equal to sine a cosine b plus cosine a sine b. Yay, trig. So here we go. This is going to be the limit as h approaches 0. So expanding in the numerator, I'm going to have sine x times cosine of h plus cosine of x times sine of h. And then I still have minus sine of x. And this is all over h. All right, now to evaluate this limit, I'm going to group some of the terms together. If you'll notice, the first and the last term both have sine x in them. So I'm going to group them together and basically split those over the denominator. So watch what I'm going to do. We have the limit h approaches 0, sine of x times cosine of h minus sine of x over h plus the limit as h approaches 0 of cosine of x times sine of h over h. All right, now pay attention to this limit. Watch this. So it's the limit as h approaches 0, right? Well, what does that mean? That means sine of x is basically a constant because h is changing, but x is not changing in the limit. Similarly, cosine of x can be treated or viewed as a constant in this limit. So what does that mean for me? I can factor it outside. Okay, so now I'm going to have sine of x times the limit as h approaches 0. I'm going to have cosine of h minus 1 over h. Okay, so if I factor out this sine x, then I have cosine h minus 1. Plus, and then again, that cosine x is going to come outside. And then I have limit as h approaches 0 of sine of h over h. All right, now look up above. Now it's time to use those limit formulas. So remember the limit as theta approaches 0, or in this case, h approaches 0, of cosine of h minus 1 over h, that's going to go to 0. So this whole term goes to 0. And so 0 times sine x is just going to be 0. Plus, and then look over here, now it's time to use the limit as theta approaches 0 of sine of theta over theta equals 1. So that means this whole quantity approaches 1. So I'm left with 0 plus cosine x times 1, which is cosine of x. So hooray, that means we found the derivative with respect to x of sine of x is equal to cosine x. Well, that was successful. Let's try the same thing. Let's figure out what the derivative of cosine x is. Any guesses? All right, let's try this one out. So I have the limit as h approaches 0 of cosine of x plus h minus cosine of x. Do we remember our cosine angle addition formula? It's a little different. So cosine of a plus b, it's cos, sine, right? Cosine a, cosine b minus sine a, sine b. Got to switch the sign on that bad boy. Okay, so here we go. Let's expand this out. So we've got the limit as h approaches 0. This will be cosine of x times cosine of h minus sine of x, sine of h, minus cosine of x all over h. And then just like last time, the terms that have cosine of x in them, I'm going to group them together. Since remember, this limit is dependent on h changing, not x. So I'm going to write this as the limit as h approaches 0. Let's factor out that cosine while we're at it. So cosine x times cosine of h minus 1 over h minus the limit as h approaches 0 of sine of x times sine of h over h. All right, same thing as last time. I'm going to take both cosine x and sine x out of the limit and then see what we have left over. So we've got cosine of x times the limit as h approaches 0 of cosine of h minus 1 over h minus sine of x times the limit as h approaches 0 of sine of h over h. Beautiful. So this is just cosine x. This whole quantity goes to 0. So it's cosine x times 0 minus sine of x times, and then this limit approaches 1. So sine of x times 1. So I have 0 minus sine of x, which is negative sine of x. So that means the derivative of cosine x is negative sine x. Is that what you guessed? All right, well, we're not going to use the definition to derive the rest. You could actually play around with it like tangent x. You could write it as sine x over cosine x and just use the quotient rule. Try it. It's not too bad. You'll be really proud of yourself. But I'll just give you the derivatives of the 6 trigonometric functions right now. So we showed derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. Derivative of tangent x, secant squared x. Derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x, secant x tan x. And lastly, derivative of cotangent x, negative cosecant squared x. These you have to burn in your brain. You have to memorize them for the entirety of your math career. They will not go away. They will not change. Some tips for you guys to notice, okay? If you're taking the derivative of a trig function and it has co in the prefix, so cosine, cosecant, and cotangent, then its derivative has a minus sign, okay? Also, derivative of tangent is secant squared, and if you just slap a co on each of those, you can see derivative of cotangent is cosecant squared. You see the pattern? And then derivative of cosecant x mirrors up with how derivative of secant x is. So derivative of secant x is secant x tan x. Similarly, derivative of cosecant x, just put a co on there. Cosecant x, cotangent x, just add the negative. Also, it should not surprise you that the derivative of tangent involves secant squared. They've been friends a long time, since trig days, right? Remember our Pythagorean identities? We have sine squared theta plus cosine squared theta equals 1. And then similarly, tangent squared theta plus 1 is equal to secant squared theta. So tangent and secant, I mean, they go way back, okay? So it shouldn't surprise you that here they are, friends again, reunited in calculus class. Here they are, hanging out. And then similarly, your last Pythagorean identity, 1 plus cotangent squared theta equals cosecant squared theta. Look who's friends hanging out again. Good old cosecant and cotangent. Okay, so once you kind of break it down this way, hopefully it'll make more sense to you. And you just have to have them quick access since you're going to be using them a lot. All right, so let's look at some examples. We're going to do some fancy derivatives now that we know how to differentiate all these trig functions. And we're still going to use product rule, quotient rule, all that good stuff from before. So first example, f of x is equal to the square root of x times sine of x. We need to differentiate. Well, we got to use the product rule, right? Can you see we have a product of two functions? Here's one function. Here's the other function. I'm going to rewrite it so it's in derivative-friendly format. So I'm going to rewrite this as x to the 1/2 times sine of x. All right? That way I'm ready to roll. So here we go. F prime of x. Now, for the product rule, you don't have to stress so much about the order that you do it in, right? Because it involves multiplication and addition. Those are both commutative. So the main thing I emphasize is that the functions take turns having their derivative taken, okay? So first, let's differentiate x to the 1/2. That'll be 1/2 x to the negative 1/2. Now I'm leaving sine of x alone. It's not his turn, okay? They gotta take turns, product rule time. Plus, now it's sine of x's turn. Okay, let's take his derivative. Derivative of sine of x, cosine x. And I'm gonna multiply by x to the 1/2. Leave him alone. It's not his turn. He already had his turn. Okay, calculus is over. Time to clean it up. So let's see here. I can factor out 1/2 x to the negative 1/2. Okay, so let's go ahead and do that. I'm going to take out 1/2 x to the negative 1/2. And I'm left with sine of x plus. Now you might be saying, what in the world? How did you take a 1/2 out of here? Well, I'm going to put a 2 right now, okay? If I divide by 1/2, that's the same as multiplying by 2. Cosine x, and then I'm going to have x to the first power, right? When I factor out x to the negative 1/2, I'm basically subtracting that from the exponent. So 1/2 minus negative 1/2 is x to the first. If you got confused right there, I took x to the 1/2 and I factored out, okay, or I divided by x to the negative 1/2. So that's x to the 1/2 minus negative 1/2, so that's x to the first. All right, almost there, almost there. It's looking pretty decent. I can just rewrite this now. The 1/2 x to the negative 1/2, I'm going to put that as 2x to the 1/2 in the denominator. And then in the numerator, let's write sine of x plus, you don't want that x at the end there, right? 2x cosine x. That way it's clear what the argument is. Argument means what you have cosine of. Okay, so it looks confusing. You know, if you have cosine of x and then there's this other x hanging out, don't do that ever. Okay, put it in the front like this. Oh, so clear. Everyone understands now. All right, good. Let's try another. That was so fun. So g of t equals 4 secant of t plus tangent t. Okay, so g prime of t. Remember, the constant just comes along for the ride. What's the derivative of secant t? Do you remember? It was only a few seconds ago, perhaps not. Secant t times tangent t. Plus, what's the derivative of tangent t? Did you say secant squared t? Correct. secant squared t. Love it. Okay, how far to clean up? Well, right now, you don't really have a lot of context as to what we do with derivatives, but I'm going to give you a sneak preview right now. Are you ready? Later on, you're going to be setting them equal to 0. You're going to be finding when the derivative equals 0 and when it's undefined. So what does that mean for us? That means you want it to be written as one expression whose zeros and undefined points can be easily identified. So it's common denominator time. I'm going to write this as 4 times, okay, secant t, that's 1 over cosine t, right? Tangent t, that's sine t over cosine t. Plus, and then secant squared t, that's 1 over cosine squared t. You guys, they already have a common denominator. I have nothing to do. This is cosine squared t, and the other one already has cosine squared t. This problem is a dream come true. So we've got 4 sine t plus 1 in the numerator over cosine squared t. And this is a beautiful place to be. Because if I were to ask you, okay, tell me where does g prime of t equal 0, you could do it. You would say, where the numerator is 0. And if I were to say, tell me where g prime of t does not exist, oh, easy. I could tell you that, no problem. So that's what's coming up down the road. But if you know that's what we're going to do with the derivatives, it'll give you a little bit more context so you have an idea how far to simplify. Okay? All right, let's do one more, just to remind ourselves how fun trig functions are. So here we have y equals 1 minus secant x divided by tangent x. So it's time to use the quotient rule. All right, so dy dx, let's sing the song. We've got low, d high. So here's low, tan x. D high is derivative of the numerator. Derivative of 1 is 0. Derivative of negative secant x is going to be negative secant x tan x. Okay, so here's high, low. This is low, d high, minus, I need high, d low. So high, just write the numerator as it is. D low, what is the derivative of tangent x? Secant squared x? Yeah, did you remember? Fabulous. High, d low, over low, low, or square the bottom, away you go, whatever your preference is. So we've got tan squared x. Okay, let's multiply it out and see how much we can clean this guy up. You might be amazed. Okay, so tangent x times negative secant x tan x, that's just negative secant x tan squared x, minus, and then I'm going to distribute this secant squared x. So here we go, minus secant squared x plus secant cubed x over tangent squared x. Okay, let's rewrite everything in terms of sines and cosines so we can clean it up a bit more. So secant x, that's negative, because there's a negative out there, 1 over cosine x. Tan squared x, that's going to be sine squared x over cosine squared x. Minus, okay, secant squared x, that's 1 over cosine squared x. Plus secant cubed x, so that's 1 over cosine cubed x. And then this is all over, you guessed it, sine squared x over cosine squared x. What to do with this? Well, first thing I notice, that's crooked, it's gonna bother me, let's fix it. Oh, much better. Also, we have a complex fraction. That's not allowed. We've got a fraction within a fraction. So we gotta multiply by the LCD of the entire expression and clear those denominators out. So what do I need to multiply by? A cosine cubed x. That's it. All right, so let's see what we got. When I distribute cosine cubed x to the first term, notice I have cosine cubed x in the denominator, so it's going to cancel out. So all I'll have is a negative sine squared x Now I'm going to distribute to the next term. I'm going to have one cosine left, right? Two of them are going to cancel. So minus cosine x. And then distributing here, just a plus 1. Beautiful. And then in the denominator, so this is gone, and I just have one cosine left over, and the sine squared x is hanging out. So sine squared x, cosine x. All right. Anything else you notice? Well, look at the numerator. I've got negative sine squared x plus 1. Do you remember 1 minus sine squared x from our Pythagorean identities? That's equal to cosine squared x. Oh, okay then. So now I have actually cosine squared x minus cosine x over sine squared x cosine x. We can factor out a cosine x from the numerator and cancel. Okay, so cosine x times cosine x minus 1 over sine squared x times cosine of x. Cancel, cancel. Very fun. So now we have cosine x minus 1 over sine squared x. But can't I replace sine squared x with 1 minus cosine squared x? Yes, I can. And that factors, that's a difference of squares. So we have cosine x minus 1 over, the denominator is going to factor into 1 minus cosine x times 1 plus cosine x. Anything else you notice we can cancel? Well, notice I have cosine x minus 1 and I have 1 minus cosine x in the denominator. So if the order of subtraction is reversed, remember you have to multiply by a negative. Here's just a fact in case you forgot. A minus b is equal to negative b minus a. So if you have a minus b over b minus a, then you get negative 1. So that's why you add the negative when you cancel. And all we're left with now, at long last, is negative 1 over 1 plus cosine x. Oh my goodness, that is a thing of beauty. Yes. So some of these will not be for the faint of heart. You do need to remember your trig. So if it's been a while, get your formula sheet out, brush up a little bit, because it's making a comeback. All right, now remember those limits we talked about at the very beginning that we used to help us get the derivatives of sine of x and cosine of x? We're going to use them now to do more limit problems. I know you missed doing limits, didn't you? So we have the limit as theta approaches 0 of sine of theta over theta equals 1, and also the limit as theta approaches 0 of theta over sine of theta equals 1. And then the other one was the limit as theta approaches 0 of cosine theta minus 1 over theta is 0. So burn these in the brain too, along with those derivatives. All right, good. Now we're going to use them for the following limits. Look at this first one. We have the limit as x approaches 0 of sine of x over sine of 4x over sine of 6x. Okay, now look at this and think, man, I wish it looked just a little differently. I really wish I had the limit as x approaches 0 of sine of 4x. And then instead of 6x in the bottom, I wish I could use this right here, right? So it would be so amazing if there was a 4x down here. Don't you agree? All right, well, I'm not going to sit around here feeling sorry for myself. I'm going to make it happen. I put a 4x in the denominator, but I can't just go willy-nilly putting 4x's in denominators. I have to multiply by 4x in the numerator over 1. That way it's like I did nothing, right? I just multiplied by 1, 4x over 4x. No, I haven't forgotten about little sine 6x sitting there. Okay, so we've got sine 6x in the denominator. Now you tell me, what do you wish? What do you wish was sitting up here? So I could use this other limit formula. Don't you wish there was a 6x there? I sure do. So make it happen and then go, oh, I multiplied by 6x in the numerator, so I got to multiply by 6x in the denominator. That way I haven't altered the expression whose limit I'm taking, okay? And then now we're ready to go. We can take this limit, okay? So as x approaches 0, sine of 4x over 4x, that goes to 1. Notice I've got this 4x up here and the 6x down there. These x's cancel. Bam, bam. Okay, looks good. So 4 is just a constant. It's not changing in the limit. Now let's move on to this next term. 6x over sine of 6x, that's going to go to 1. And then the last term's just a constant. So what am I left with after I take this limit? I just have 1 times 4 times 1 times 1/6. So 4 times 1/6, that's 2/3. All right, and I do need to see all this work. Just slapping the answer 2/3 on there doesn't show that you understand anything. So make sure you show all these steps. Okay, let's look at another example. Here we have limit as theta approaches 0 of cosine theta minus 1 over sine theta. If you just try to plug in 0 for theta, cosine of 0 is 1, so you'd get 0 over 0. No good. Okay, look at what we have. Look at the limit formulas. I see cosine theta minus 1, just like here, but what's missing? There's no theta in the bottom, right? And then again, I see sine theta in the denominator, just like here, but there's no theta in the numerator. So I wish there was a theta in the denominator. I wish there was a theta in the numerator. Let's make it happen, people. I'm going to multiply by theta over theta. So now watch how we're going to regroup it. I'm going to write this as the limit as theta approaches 0. I'm going to put cosine theta minus 1 over theta times theta over sine theta. Oh, and now we're so happy because as theta goes to 0, this term goes to, to 0. And theta over sine theta goes to 1. Now can I evaluate this limit? Do we know what 0 times 1 is? I hope so. It's just 0. See? Wonderful. Okay, one more. We have the limit as t approaches 0 of sine squared 3t over t squared. Okay, so notice the numerator squared, the denominator squared. I'm going to write this as the limit as t approaches 0 of sine of 3t over t quantity squared. All right, great. Now, what do you wish was going on in the denominator? The argument here has to match, right? What's on the other side? So I'm missing a 3. We're going to fix it. We're not defeatists as calculus students. We fix situations. So I have sine of 3t. There already is a t, but I'm going to add a 3 in here. Well, if I add a 3 in the denominator, I got to multiply by 3 in the numerator. Just over 1, right? Because I want them to still have the same value, and this is all squared. Okay, lovely. So now we can go ahead and take the limit. As t approaches 0, sine of 3t over 3t, that approaches 1. And then 3 over 1, that's just a constant. So what do we have here? We have 1 times 3 squared, which is just 9. Beautiful. So that concludes the lesson. Hope you enjoyed it. Make sure you do flashcards or whatever you need to do so that you have these trig functions and their derivatives all memorized. Review your Pythagorean identities and all that good stuff from trig too, because you're going to need it to clean up these derivatives, all right? So make sure you give the video a thumbs up, subscribe if you haven't. Up next is the chain rule. It'll be fun, I promise. Stay tuned.